We're going to take a look at the properties of real numbers. We're going to take a look at what the property. So first, the first property we talk about is reflexive. A equals A. Why might that be useful? What's that even for? For doing what? When you have a... Okay, if you have a system of equations, what else? What else? What do you do when you get your answer usually? You check your answer. And then when you check it, you're using the reflexive property, you make the statement that either or both sides of the equations are equivalent to one another.
Or when you have a series of equations like that, and the first equation solves for A.
Hold on, you're going to see that in a minute. Look at the third one. I think we're going to the third one, right?
Yeah.
Chain rule like that, if one is equal to something else, yeah, that's a different law.
That's what like triangle is. That's like more geometry.
It's both geometry and algebra, actually. Yeah, because you're thinking geometry because when you did like perfect triangles, equivalent or congruent, yeah, it works that way, but it's also algebraic. Symmetry just simply says that we can do what to the equation? Yeah, doesn't matter which side's on which, right? Is that clear? We all should know that by now. The third part, transitive, is what Nico was mentioning a minute ago. And the transitive we know. It's the chain rule. Okay, if you're the same height as your friend, and your friend is the same height as another person, all three of you are the same height. So if A equals B and B equals C, then clearly A equals C. All three are the same. Additive property here. We know that if we have A equal to B, we can add the same thing to both sides of the equation, and it is still true. 7 equals 7. If I suddenly add 3 to both sides, now we've got 10 equals, and then just doing a math for chemistry. And then finally, multiplicative. Okay, why do I not have subtraction and division? Where are they? Where's subtraction and division, Alex?
They don't work out the
This can be last here, but multiplication is the same thing. I mean, it's not the same thing. You have to multiply it by negative.
By what?
By negative, or by reflexive, fraction. So
To get what?
instead of dividing by a half, you multiply by 1/2.
So what he's getting at is that multiplication and division are linked, right? Division's definition is multiplication by the, what's the term?
Oh, reciprocal.
Reciprocal, very good. So can anybody help me out with the one with addition then? What's going on there? Because multiplication covers multiplication and division.
Addition is adding.
Yeah, exactly. Subtraction is defined as adding the opposite. So you don't need to list the subtraction property of equality or multiplicative property, division property of equality, because they're embedded in these last two. Okay, they're already there. They're not their own separate laws or equality properties. Okay. We also know some of our field properties. You've learned these when you were in like probably 7th grade math, 6th grade math, even sooner maybe. Commutative law. How do you remember what commutative law is? I know a lot of you know it, but what's an easy way to remember it? How many people take the train here at school? Alright, now you commute in the morning, then when you commute you go one way, and then when you commute home you go the other way, right? So you literally just switch directions. That's what you're doing here. You can say you can switch the two. A plus B equals B plus A. A times B equals B times A. Do these two properties hold true for division and subtraction? It does not. I said two properties. It's one property. It does not hold true for division or subtraction. Why? Why?
Because if you put a subtraction or like a negative number first or second, it may change the answer.
Exactly. If you switch the order when it's subtraction, you get the opposite of the answer you want. 5 minus 3 is 2, but 3 minus 5 is negative 2, right? You get the opposite when you switch the order. Division, you just get the reciprocal of what you would have had, right? If you flip the top and bottom there. Associative, think about grouping, right? The grouping of parentheses. Who do you associate with? Who is your group of friends? What kind of people do you associate with? So when you think of associative, think of grouping. So you can see here clearly that A plus B is grouped in the first part, but then after that, B plus C is grouped in the second part here. And then the same thing goes for multiplication. A times B is grouped here, but B times C is grouped here. It doesn't matter which one you do first. Okay? Does not matter. All right, inverse properties. For additive, A plus negative A gives you 0. Okay, A plus negative A gives you 0. So what we could say here was, wait a minute, because we'll get to identity before we get to that. And multiplicative, A times its reciprocal gives you 1. Okay, A times its reciprocal gives you 1. A plus its opposite gives you 0. For identity, though, we're going to see these two numbers appear again. So the 0 that's here for identity of addition occurs because when you add 0 to anything, what happens? It stays the same. Nothing happens. When you multiply 1 by anything, what happens? Same thing, okay? Thus, we call it identity because it's identical. So the identity elements are 0 and 1. 0 for addition, that's why it's in red here, and 1 for multiplication. And finally, distributive. Distributive you've seen this many times. Just make sure you take this number that's out in front and multiply it by all the terms on the inside. This is one example, but I could have this, right? And all of these need to get distributed. Okay? So we have to remember to distribute whatever's on the outside. It's called a scalar. When you hear about the term scalar versus vector, the scalar or the constant on the outside needs to get multiplied by every single term on the inside. Okay? All right, good. So example 1. Let's take a look at example 1 here. So we've got 14 times the quantity 3xy squared times the quantity 5w to the 4th. So we should probably use our associative law and regroup this, right? Make sense of the numbers in one part and the variables in the other. So I'll start by doing that, just regrouping it. Now you don't need to really write this out if you know this, obviously, which you should by now. So you can just multiply those three numbers together. Okay, 3 times, let's do 14 by 3 first. That'll give us 42. 42 times 5 is 210, should be? 210, yes? What about the other part? X, y to the second, w to the 4th. Stays the same. Okay, if we don't have variables that have the same base, we cannot simply add the exponents. Had it been x squared times x to the 3rd, we could rewrite that with like something like x to the 5th. Anyone know today's a B-day, correct? All right, so we'll finish up with this last example for today, and then we'll take up. Let's take a look at this. We want to justify each step along the process. So take a look. From the original to part A, what did we do? Starting from the original, go down to part A. What property did we use to get from the original to part A? To part A. Sarah? What is it? Distributive. This 2 was distributed to both of these, giving us this expression right here. So this is the distributive property. From step A to step B. From step A to step B. It's almost like, why would I do that? You wouldn't do this, but we need to know what is physically happening. What's the only difference in A and B? It is identity. What's the only difference though?
It's 1y.
Yeah, the 1 times the y. You're multiplying something by 1, so it's the identity property of multiplication. Now, again, when you're doing things mathematically, you're not going to be thinking about every single step along the way, right? You're just going to simplify now, and that's fine. But we need to know why we can do that. That's the whole theory behind it. From B to C, what happened? What happened from B to C? Alex? Not commutative. The associative. Can you explain why you now understand the second time through?
Because the associative is like for groupings.
Very good, for grouping. We see that the parentheses went from being around here to being around here. So all we did was change parentheses because there's addition. So associative of addition. from step C to step D. Step C to step D, and this is not obvious. This is kind of a trickier one. Step C to D.
It's like the inverse of distributive?
Very good. It's the opposite of distributive here. So we could technically still write distributive. It's pretty much factoring, right? You factored out a y. Think about it this way, right? This y is in both terms. You factored it out, leaving you with the 1 plus the 2 here. So when you factor something out, it's the opposite of distributive, okay? Factoring is the opposite of distributive. So it's still called the distributive property, though. And then finally, from D to E. From D to E. This is one that is not obvious at all, because it's not one of the ones we need to go over. We replaced 1 plus 2 with the number 3. So what did we do? We blank. Simplified, or, I'll take that, or what?
Combine my terms.
Yes, what's the term for that? When you replace the numbers 1 plus 2 with an equivalent value of 3. Substitution. You substituted a 3. Okay? But simplification or substitution is fine. You can write out combining like terms, but this, again, would be substitution. Okay? So determine whether the set S is closed under the 3 operations. Try it on your own. Try it on your own. So look at the set. It's the set of multiples of 3 that are positive. That's the set we're looking at here. Positive multiples of 3. You got multiplication, addition, and division to look at for this one. Again, the question is which of the 3 sets, or which of these sets is closed, or which of these operations, rather, is closed for the following set. Again, it's not closed, provide an example of when it would not be closed. Starting with multiplication. Multiplication, what do we have? I want an answer and a reason for your answer. Some sort of reasoning as well. Yeah.
I'm kind of confused. Are we trying to determine like what the pattern is of X?
Not what the pattern is, but remember what we did with integers a minute ago? We said like if you add 2 integers, you end up with an integer still, so it's closed under addition. But when you divide 2 integers, you always get an integer. So it's not closed under division. Now instead of the set of integers, we're using this set right here. 3, 6, 9, 12, 15, the multiples of 3. And the question is, are the multiples of 3 closed under multiplication? Are the multiples of 3 closed under addition? Are the multiples of 3 closed under division? So think about the possible combinations of the multiplications here, or the operation of multiplication, and what happens as a result. Can anyone explain part A? How about an answer for part A without an explanation? Is it closed or is it not? At least that. Is it closed under? It is under multiplication. I agree with Will. It's definitely closed under multiplication. Can somebody give me some sort of reasoning as to why? Yeah.
Because if you multiply two of the numbers, you still get a multiple of 3.
Yeah, whenever you multiply something that has a 3 and it has a factor, you're going to get a multiple of 3. Think about it for a second. It does not matter, but every one of these numbers can be broken into its prime factors. The next number is 12, isn't it? And that's 3 times 4. So what do you recognize? Every single number in this set, since they're multiples of 3, can be broken down to factors with 3. So as a result, if you multiply any of these, you're going to be multiplying the number 3 somewhere in there. Pick a number that's a multiple of 3 much later. 3's got to be in there. 45 times 60. I have no idea what the answer is, but I know that it's going to be a multiple of 3 because 45 can be broken into 3 times 15. And 20 is 3 times, and 60 is 3 times 20. So as a result, since all of the multiples of 3 can be factored into something with a 3, you most definitely have an answer that will always be a multiple of 3. Okay, all the products you would get would have 3 as a factor. That's how you know. That's how you know that the set of multiples of 3 is closed for multiplication. All right. Addition. What do we have for that? What do we have for addition?
I say it's close
And why?
because when you add 3 and 6, you get 9, and you keep on adding, you keep on getting a multiple of 3.
Yeah, anytime you add a multiple of 3, you get another. Now, let's go back to the concept of factors once again. Think about it. Pick any two numbers. Think about, let's see, 24 plus 18. Both multiples of 3, right? Will yield what? 40, where are we at? 42. And 42 is clearly a multiple of 3 because 4 plus 2 is 6. Do you know that trick, by the way? Anyone know that trick? To see if something is divisible by 3, what do?
You add two numbers and you see if it's like 2 divided by 3.
Yeah, add the digits. Pick a 3-digit number. 392. 3 plus 9 plus 2 is not a multiple of 3, right? 3 plus 9 is 12 plus 2 is 14. So 392 isn't divisible by 3. It works with 3s. It's a trick for 9. Also, there's a few tricks for divisibility. Anyway, back to the question. Break up 24 and 18 into their prime factors, or into factors of 3. 24 is 3 times, and 18 is 3 times. So I could factor out a 3, can't I? And what do I get? 3 times the quantity 8 plus 6. Well, that's really just 3 times 14. That's where that 42 came in. But what I want you to pick up on is this. When you add two things that are multiples of 3, you could break it into its factors and factor the 3 out. The minute you factor the 3 out, it doesn't matter what this number is. It makes no difference. This can be anything. This can be anything. And as a result, any positive, because we're working with positive numbers here. This can be any positive value, let's say 8 plus 6 here. This could have been 8 plus 2. This could have been 8 plus 3,000. This could have been 8 plus 10,244. It doesn't matter because you're multiplying by 3 in the end. So your answer, because you were able to factor out 3, has got to be a multiple of 3 in the end for addition. How about division? Jeffrey. How come? Give me an example to prove it. 3 divided by 9 equals 1/3, which is not in the set. Okay, very good. 3 divided by 9 simplifies to 1/3, and then is not in S. It's not in the set. So one example that does not work proves the set is not closed for all numbers in that operation. So tonight when you work on this homework over the weekend on this section, you're going to be asked questions like, is the set of natural numbers closed under this operation? Yes or no? Reasoning. Whether yes or no, for both. Okay? Questions on this topic of closure? I didn't see a lot of hands shoot up before when I asked, so you're sure there's no questions? Okay. All right. Let's take a look quickly so you know. Okay? So, again, what I keep telling you guys, every night you do homework, there's going to be some review questions. Here's the review portion right there. When you get to chapter 7, you might be doing homework problems from chapter 2, but only like 2 or 3 of them. See, there's only like 2 or 3 here. There's always going to be a review portion. I cannot tell you how many students last year neglected to do that. Not only would they get a 4 or 5 on their homework because they didn't complete their homework, but it really helps a lot to track back to review. It's like you're studying for the midterm all the time. It's like you're studying for the final all year long by doing these older problems once in a while. Okay? So please don't ignore them just because they're not based on the topic we just learned, especially when we're, again, in like chapter 7 and I give you 2 problems from chapter 3. If you forget how to do it, what do you need to do? Yeah, go back and look in your notes. Go back and look in the text. Figure out what it was in chapter 3 that you're confused on, or come ask me. If it's not held in your memory at the end of the year, you can't do it on the final, right? Final is the entire year. The entire year. Okay.